You need 9 square feet of glass mosaic tiles to decorate a wall of your kitchen. You want the area of the red tiles to equal the combined area of the yellow and blue tiles. The cost of a sheet of the glass tiles having an area of 0.75 square foot is $6.50 for red, $4.50 for yellow, and $8.50 for blue. You have $80 to spend. How many sheets of each color do you need to purchase? In order to find a system of equations, we will use each line of the problem to write each equation. Our variables will be r for the number of red sheets, y for the number of yellow sheets, and b for the number of blue sheets. The first line means that r plus y plus b is equal to 9, since the total is 9 square feet. However, since each sheet has an area of 0.75, the variable's coefficients will be 0.75. The second line shows that r is equal to y plus b, but in order to make this into a usable equation as a matrix, it can be rearranged to negative r plus y plus b is equal to 0. The third line means that the price of each color sheet will be that color's coefficient in the equation, and since the total money is 80, the equation will be equal to 80. First, we're going to solve the problem through inverses. In the first step, we're going to write down our system of equations. Using the system of equations, we're going to make two matrices. One where the coefficients of the variables, r, y, and b, will become matrix A, and a second where the numbers on the right side of the equation, 80, 9, and 0, will become the answer matrix. Next, we're going to set up the problem by multiplying matrix A by the blank variable matrix r, y, and b, and that will be equal to the answer matrix. Next, we will use our calculator to find the inverse of matrix A and multiply both sides of the equation by the inverse on the left-hand side. Lastly, we will use our calculator to solve for the variable matrix. The inverse and matrix A cancel out, and the answer matrix and the inverse multiply to equal 6, 2.5, and 3.5. This means that you have 6 red sheets, 2.5 yellow sheets, and 3 blue sheets. Now we're going to move on to substitution. First, we're going to write out a system of equations which have been reorganized a little bit to make the substitution easier. Then we're going to use r equals y plus b and plug that into the other two equations. When we solve for the first equation, we get our answer to be 11y plus 15b equals 80. Then when we solve for the second equation, we get y is equal to negative b plus 6. So now when we plug in y is equal to negative b plus 6 into 11y plus 15b is equal to 80, and then solve for b, we get our answer to be b is equal to 3.5. When we plug in 3.5 into y is equal to negative b plus 6, we get y is equal to 2.5. And when we plug in 2.5 and 3.5 into r plus y plus b is equal to 12, we can solve for r and get 6. We chose substitution because we couldn't figure out how to work with elimination, and substitution was the easier way for us. Since one of our equations is r is equal to y plus b, it made substitution to be the more clear and simpler option to use. Also, having 3 equations and variables to solve for made elimination a lot more complicated. In the end, we chose substitution because it was simpler, easier to understand, and our equations fit that method. Lastly, to solve, we're going to use Cramer's rule. First, we're going to write down our system of equations. Using the system of equations, we're going to make 4 matrices. The first is a parent matrix, where all the coefficients of all the variables are represented. Next, we're going to make an R matrix, where the R coefficients of the variables are replaced with 80, 9, and 0. Next, we're going to make a Y matrix, where the Y column is replaced. And then we're going to make a B matrix, where the B column is replaced. Next, we're going to find the determinant of each matrix. The determinant of the parent matrix ends up being 6, the determinant of the R matrix ends up being 36, the determinant of the Y matrix ends up being 15, and the determinant of the B matrix ends up being 21. In order to solve the last step of Cramer's rule, we have to divide the determinants of matrices R, Y, and B by the determinant of the parent matrix. When we solve for R, we get 6 red sheets. When we solve for Y, we get 2.5 yellow sheets, and when we solve for B, we get 3.5 blue sheets. Our preferred method to use is inverses, because inverses are generally the simpler and shorter way to solve. There's a lot less tedious work involved to solve through, especially when using a calculator. In our inverse problem, setting up the problem was very short, simple, and straightforward, unlike Cramer's rule, in which it took a lot of time to write down all of the matrices and determinants. Also, the process of solving the inverse was short and easy to understand and keep track of, unlike the substitution, in which it had a lot of different and confusing steps when we plugged in new variables into new equations.